Welcome, nocturnal minds aboard. Your learning journey starts now. So, building on our discussion of how we carve up the world into space-time and categories, let's explore a concept that seems to underpin much of that structure: symmetry. When we talk about symmetries in nature, we often picture perfect shapes, think crystals or planets orbiting the sun. There's this intuitive feeling that these symmetries hint at some deep, underlying simplicity and harmony in the universe. The idea isn't new. The ancient Greeks were already pondering it, linking it to beauty and unity. A classic example is Johannes Kepler. He was obsessed with finding mathematical patterns in the cosmos, believing God designed the solar system like a clockwork mechanism. His Mysterium Cosmographicum tried to fit the planetary orbits onto nested platonic solids. It didn't quite work out numerically, but that quest for mathematical harmony didn't stop him. It actually pushed him to dig deeper, eventually leading to his groundbreaking laws of planetary motion. Interestingly, while Kepler looked for static geometric forms, later thinkers like Hermann Weyl pointed us towards a shift. Maybe the real action, the true harmony, lies not just in objects, but in the dynamic laws governing them. So, what exactly is this symmetry thing in physics? At its heart, it's about invariance. If you do something to an object or a system and it looks or behaves the same afterwards, it's symmetric under that operation. Think of a cylinder, spin it around its central axis, and it looks identical. A sphere is even more symmetrical. Spin it any way you like, and it still looks the same. They also have reflection symmetry. Hold up a mirror, and they look like themselves. Now, when we talk about laws of physics, the idea is similar but applied to observers or frames of reference. Einstein's principle of relativity is a prime example. It states that the fundamental laws of physics, and even the speed of light, must appear the same to any two observers moving at a constant velocity relative to each other. Whether you're on a train or standing still on the platform, the laws governing motion should seem identical. This wasn't just about constant speeds. General relativity extended this to accelerating and rotating observers too. The famous equivalence principle says that the forces you feel from acceleration or rotation are fundamentally indistinguishable from gravity. So, symmetry here describes how the rules of the game stay consistent across different perspectives or conditions. This connection between symmetry and dynamics is crucial. Symmetries tell us how physical systems respond to changes, how they behave under different influences. Remember the sphere. Its equation describing its shape doesn't change if you rotate it. So, both the physical object and its mathematical description are invariant under rotation. To really harness the power of symmetry, we need a language to describe these transformations precisely. That's where group theory comes in. Don't worry, we won't get bogged down in the math. But the idea is that a group is a set of things that can be transformed into each other using specific rules or operations. For any physical object or law, the collection of all transformations that leave it unchanged forms its symmetry group. So we can now say, a physical object or phenomenon obeys a certain symmetry if the fundamental laws governing it remain the same no matter which transformation from that symmetry group you apply. It's like saying the rules of the game don't change if you rotate the playing field, or if you swap certain players according to specific rules. Let's look at some concrete examples. Consider spatial translation symmetry. This means there's no special point in space. The laws of physics should be the same whether you're in London, Toronto, or orbiting Jupiter. Similarly, time translation symmetry means the laws don't depend on when you perform an experiment. Run the same experiment today or tomorrow. Assuming nothing else changes, you should get the same results. These symmetries aren't just philosophical curiosities, they have profound consequences, thanks to Emmy Noether's brilliant theorem from 1918. She showed that every continuous symmetry of the laws of physics corresponds to a conservation law. Think about it. Because the laws are the same everywhere in space, momentum is conserved. Because they are the same everywhere in time, energy is conserved. And because they are the same under rotation, angular momentum is conserved. It's a beautiful link. The invariance of the rules leads directly to the constancy of certain quantities in the universe. The conserved quantity is what remains invariant during the process described by the equations. Now symmetries come in different flavors, which helps us understand their role better. We can categorize them in a few ways. First, global versus local. A global symmetry is like a uniform transformation applied everywhere at once, say shifting the entire coordinate system. A local symmetry is trickier. The transformation can be different at different points in space or time. Imagine twisting a fabric. The twist might be stronger here and weaker there. Second, continuous versus discrete. Continuous symmetries involve transformations that can take on infinitely many values, like rotating a wheel by any angle. Discrete symmetries involve distinct steps, like rotating a square by 90 degrees or reflecting an image. Finally, geometrical versus internal. Geometrical symmetries relate to the structure of spacetime itself, translations, rotations, reflections. Internal symmetries deal with the intrinsic properties of particles or fields, like charge conservation or the mixing of particle types, rather than their position or motion. These distinctions become really important when we talk about modern physics theories. Since the 1960s, symmetry has become absolutely central to constructing physical theories. The big idea is that all fundamental interactions arise from something called gauge fields. And the structure and behavior of these fields? They are dictated entirely by the requirement of local symmetry. This idea has roots going back to Hermann Weyl in 1918, who initially thought about scale invariance. It didn't pan out, but Fritz London later realized the key was phase invariance for electromagnetism. Here's the kicker. If a theory is only invariant under a global transformation, you don't need new forces. But if you demand invariance under a local transformation, meaning the transformation can vary from point to point, then you absolutely must introduce new force fields, called gauge fields, to maintain that symmetry. These gauge fields interact with whatever quantity is being conserved by that symmetry. Take electromagnetism. The local U1 symmetry means the phase of the electromagnetic potential can vary independently at each point in spacetime. To make the physics look the same locally, despite this varying phase, you need the electromagnetic field itself carried by photons. The conservation of electric charge is the conserved quantity tied to this U1 symmetry, and the photon field is what ensures the local symmetry holds. It's incredibly elegant. The symmetry requirement forces the existence of the force carrier. This gauge idea wasn't just for electromagnetism. The unification of the weak nuclear force responsible for radioactive decay with electromagnetism into the electroweak theory relied heavily on this. The symmetry here is a local internal symmetry. It's internal because it deals with the identity of particles, not their location in spacetime. Think quantum mechanically. A particle can be in a superposition state, like being neither purely an electron nor a neutrino until you measure something that distinguishes them, like electric charge. The electroweak theory posits that the fundamental laws are unchanged if in the equations we replace electrons and neutrinos with mixed states. This local symmetry, this ability to mix particle identities independently at each point, again, requires the introduction of gauge fields. In this case, it's the W and Z bosons that mediate the weak interaction. Another famous example is color symmetry in quantum chromodynamics, QCD, the theory of quarks. Quarks come in three colors, red, green, blue, and there's a local symmetry among them. This requires gluon fields to mediate the strong nuclear force. It's a recurring theme. Local internal symmetry implies the existence of a corresponding gauge field and force. Now things get even more interesting with spontaneous symmetry breaking, or SSB. This happens when the equations describing a system have a certain symmetry, but the actual physical state the system settles into breaks that symmetry. Think of a perfectly balanced pencil standing on its tip. The laws governing it are rotationally symmetric. But when it falls, it points in a specific direction, breaking that symmetry. Or consider a permanent magnet. Below a certain temperature, iron atoms spontaneously align their magnetic moments, creating a net magnetization in one direction. The underlying laws of electromagnetism are perfectly symmetric with respect to direction, but the resulting magnet breaks that symmetry. Wimberg calls this very Platonic. The reality we observe is just an imperfect reflection of a deeper, more symmetrical reality hidden in the equations. The electroweak theory provides a crucial example. The unified theory before SSB had a higher symmetry. After SSB, the photon becomes massless, while the W and Z bosons acquire mass. The mechanism explaining this involves the Higgs field and particle, though confirming the Higgs experimentally was a major undertaking. SSB is vital for understanding various phases of matter and particle masses. This incredible success of symmetry principles raises some deep philosophical questions, especially concerning mathematics. Group theory, particularly Lie groups like SU-SEN, proved remarkably powerful. Physicists like Gell-Mann used it to classify the zoo of elementary particles discovered in the 50s and 60s, creating the eightfold way, and even predicting the existence of the omega- particle based on gaps in the symmetry pattern. Eugen Wigner famously lamented the unreasonable effectiveness of mathematics in physics. Concepts developed purely for mathematical elegance, like group theory or Hilbert space, turned out to be essential tools for describing the physical world. Why? One simple answer is that the world itself is structured in symmetrical ways, and mathematics is just the language we use to describe that structure. This suggests an ontological claim. Symmetries aren't just useful tools, they are fundamental features of the physical world. The success of symmetry arguments could be explained by inferring the existence of these symmetries as real aspects of nature. Of course, philosophers have critiqued this inference, arguing it needs stronger empirical grounding. So, can we observe symmetries directly? Brady and Brown tried to distinguish. They suggested a symmetry has direct empirical significance if two conditions hold. First, the transformation itself must lead to a scenario we can tell apart empirically. Second, the internal dynamics of the transformed and untransformed systems must be empirically indistinguishable. Think of Galileo's ship inside the cabin. You can't tell if the ship is at rest or moving uniformly relative to the shore. That's direct evidence for spatial translation symmetry. For global continuous symmetries, they argue direct observation might be possible, at least theoretically. However, for local internal symmetries like gauge symmetry, the picture is murky. The required transformations, like varying the phase of a field locally, aren't physically implementable or observable in the way Galileo's experiment was. So, the argument goes, local symmetries only have indirect empirical significance. Their value comes from the consequences they entail, like the existence of gauge bosons or conservation laws. But this distinction is controversial. What counts as direct access? And doesn't assuming symmetries have some physical status already make the direct versus indirect debate somewhat circular? Hidden symmetries, like those broken spontaneously, bring similar interpretive headaches. The equations might scream symmetry, but the physical reality looks asymmetric. Take the Higgs mechanism again. We believe the electroweak symmetry is broken, giving particles mass, but the mechanism involves the Higgs particle or field. Our belief in the hidden symmetry of the original theory is deeply tied to whether the Higgs mechanism itself is a legitimate physical explanation. If the Higgs turns out to be problematic or unobservable, does that cast doubt on the symmetry itself? It blurs the lines. There's a crucial difference here. Asking whether the Higgs particle exists is an empirical question. We can in principle search for it. But asking whether the underlying hidden symmetry is a fundamental feature of reality, beyond the observable consequences, starts to feel more like metaphysics. Philosophy of science then faces the task of carefully distinguishing between what we can test empirically and what might be deeper metaphysical claims about the structure of the universe. So, wrapping up the symmetry section, it's clear that symmetry principles are absolutely central to modern physics. They provide a powerful framework for understanding the structure of physical models and theories, and they seem intimately linked to the fundamental forces and particles that make up our universe. From the invariance of physical laws under different transformations to the emergence of conservation laws via Noether's theorem, and even to the intricate dance of gauge fields and forces, symmetry is a guiding principle. While the exact ontological status of symmetries and the best way to justify their use in physics remain debated, there's no denying their immense heuristic and predictive power. It seems symmetry is far more than just a mathematical convenience. It appears to be woven into the very fabric of physical reality. For those interested in digging deeper into the fascinating world of symmetry in physics, there are several excellent resources. For foundational texts, Wells' work is essential reading, as is Steven Weinberg's discussion of the role of symmetry. For a broader perspective, Barrow and Pagels offer accessible accounts. Vincent Ike's book provides a scientifically rigorous yet engaging overview without heavy mathematics. If you want to trace the historical development, Donsel's collection is invaluable. And for a more technical mathematical treatment, Acheson's book is highly recommended. These should provide a good starting point for further exploration. Alright, shifting gears now to a different but equally profound philosophical puzzle, truth-likeness. At its core, any inquiry, scientific or otherwise, aims to uncover truth. Success is measured by how well we approximate that truth. Scientific inquiry has been remarkably successful, transforming our lives in countless ways. Yet, paradoxically, history is littered with once promising theories that were later proven false. Think about the Ptolemaic model of the heavens, or even Newtonian mechanics in cosmological contexts. So, the question arises, how can science claim to be progressing towards truth if it constantly generates falsehoods? One reaction might be to ditch the goal of truth altogether and focus on practical outcomes like empirical adequacy or technological utility. But another path, championed by thinkers like Karl Popper, is to embrace the concept of truth-likeness. The idea is that even false propositions can be ranked by how close they are to the truth. If some falsehoods are better approximations than others, then scientific progress through successive falsification is still possible. Intuitively, we feel like some falsehoods are better than others. Saying there are 7 planets feels closer to the truth than saying there are 5, even though both are false. Similarly, among truths, knowing there are between 7 and 9 planets feels more informative, closer to the whole truth, than just knowing there are between 1 and 100. And sometimes a falsehood can feel closer to the truth than a trivially true statement, like the tautology, there is some number of planets. This suggests a finer-grained structure than just true or false. The problem of truth-likeness, then, has multiple facets. There's the logical problem. How do we formally define this concept and understand its properties? There's the epistemological problem. How can we actually know or assess the degree of truth-likeness of a proposition? And there's the value problem. Why do we care about truth-likeness? What makes it valuable? These aren't isolated issues. Progress on one often illuminates the others. Why did this problem really take center stage in philosophy? It seems to hinge on a particular combination of 3 stances which are relatively recent developments in epistemology. First, realism, the belief that there is a truth about the world, independent of our knowledge or ability to verify it. Second, fallibilism, the recognition largely driven by the history of science showing countless false starts that we cannot be certain we will ever know the truth, even in the limit of inquiry. Third, optimism, the hopeful affirmation that despite our fallibility, scientific inquiry can genuinely make progress towards that truth. Only when you hold all 3, realism, fallibilism, and optimism, does the problem of truth-likeness become truly pressing. Realism demands truth as the goal. Fallibilism admits we won't reach it easily, and optimism insists we can still get closer. This combination forces us to grapple with how falsehoods can be ranked in terms of proximity to the unattainable truth. It's no surprise that Karl Popper, the philosopher most associated with embracing fallibilism and realism while maintaining scientific optimism, was the first to tackle truth-likeness systematically. His approach, the content approach, rests on 2 pillars, truth value and content. Content, for Popper, is inversely related to logical probability. A highly improbable theory has high content. He made a crucial distinction between epistemic probability, which is about how likely a proposition seems to be given our current knowledge, and verisimilitude, which is about how close a proposition is to the actual truth. Popper argued that, all else being equal, greater content correlates with greater truth-likeness. His formal definition was quite specific. Proposition A is closer to the truth than B if and only if A entails all the truths that B entails, and B entails all the falsehoods that A entails, with at least one of these containments being strict. Essentially, A captures more of the truth and less of the falsehood compared to B. Popper's account had some appealing features, like ensuring the complete truth is closest to itself and ranking stronger true theories appropriately. However, it also faced significant challenges. Firstly, it ruled out any falsehood from being closer to the whole truth than any truth. So, Newton's theory of motion, despite being false in some regimes, couldn't be said to be closer to the truth than a trivial tautology, like something happens to objects. Secondly, the content principle for truths rarely applies cleanly in real-world scientific disputes, where rival theories are often incompatible. Thirdly, and perhaps most problematically, it led to incommensurability among falsehoods. As Miller and Tichy showed, you can't improve the truth content of a false theory without also increasing its falsity content. Attempts to fix this, like dropping the falsity content clause, led to disastrous results, like implying that adding any random falsehood to a known falsehood would make it closer to the truth. Other weighting schemes produced counterintuitive rankings. Clearly, just using truth value and content wasn't enough to capture our intuitions about truth likeness. This led to the development of the likeness approach, contrasting sharply with the content approach. Instead of just classifying possible worlds as actual or non-actual, the likeness approach ranks non-actual worlds based on their closeness or similarity to the actual world. The idea is that the truth likeness of a proposition depends on the closeness of the possible worlds within its range to the actual world combined with some logical weighting. We could use qualitative measures, like looking at the minimum or maximum distance of worlds in the proposition's range from the actual world. Or we could use numerical measures like the average distance. Let's consider a simple weather example with states hot, rainy, windy, and suppose the actual world is hot, rainy, windy. We can rank complete propositions like H and R and W being true, and incomplete ones like H or H and R. Judgments like these can be used to test different theories of truth likeness. For instance, measures based on min A, the closest world, and max A, the farthest world, can capture many intuitive rankings, though they might violate the content principle for falsehoods. Given the strengths and weaknesses of pure content and pure likeness approaches, various hybrid models emerged, trying to capture the best of both worlds. One early attempt was the min-max average, which takes a weighted average of the minimum distance min and maximum distance max A within a proposition's range. This allows comparing all propositions and acknowledges that some falsehoods can be closer than some truths. However, it fails the content principle for truths. Adding a world far from the actual world to a true proposition can decrease its average distance, making it seem more truth-like. Niiniloto proposed using the sum of distances sum A instead of max as a content measure. Arguing sum is a better indicator of logical weakness or lack of content. The resulting min-sum average measure seems more promising. It generally satisfies the content principle for truths, allows comparison between all propositions, and handles intuitive cases better. Interestingly, Ward and Franson invoked Arrow's impossibility theorem from social choice theory to argue that finding a perfect compromise between purely qualitative content and likeness approaches might be fundamentally difficult. Suggesting any apparent synthesis might ultimately lean towards one paradigm. Another major challenge for truth-likeness theories is frame dependence. Aronson and Silas pointed out that some measures like overall average distance using symmetric difference yield truth-likeness values that depend on the number of basic states n in the framework. A simple atomic proposition, H might have a truth-likeness of n plus E divided by Rn, which approaches Rfng, the level of a tautolese, as n gets large. Niiniloto countered that truth-likeness should naturally depend on the context, as the target truth itself might change. He suggested using absolute closeness measures like T-F for a conjunction of T true and F false atomic propositions which are independent of n. But Miller raised another issue analogous to Goodman's Grube-Lean problem. Define new states like Minnesota equals hot if and only if rainy. Depending on whether you take hot, rainy, windy, or hot, Minnesota, Arizona as your basic states, the calculated distances between worlds can reverse. This highlights the difficulty of determining what counts as a natural or basic property. Is it a priori or determined by mature science? Either way, It suggests some conditions are more fundamental than others, and they should determine similarity relations, potentially leading to incommensurability between different theoretical frameworks. Much of the work on truth-likeness has been somewhat piecemeal, evaluating proposals against specific intuitions. In contrast, concepts like goodness and betterness have received more systematic treatment in value theory, exploring ideas like separability and additivity. Since truth-likeness is valuable, perhaps its logical structure can shed light on ours, and vice versa. Hardy explored this connection using the recombinant values principle. This principle states that an ordering of worlds can be represented by an additive measure if and only if the value of a composite world depends only on the values of its basic components, regardless of how they're combined. Applied to truth, this suggests the cognitive value of a piece of information, like, it is hot, might be independent of other facts, like, whether it is rainy. Kant famously argued value isn't always additive. Happiness adds to a saint but subtracts from a villain. But we can reframe Kant's ordering in terms of virtue and desert, making it additive. This suggests that whether value is additive depends on what we take as the fundamental axiological factors. Similarly, perhaps we can identify a set of basic states such that an intuitively given ordering of truth-likeness becomes additive. This could help us choose the right framework for measuring likeness. After decades of intense debate, there's still no single universally accepted theory of truth-likeness. Graham Sillows, reflecting on this, suggested perhaps we should give up on formal analysis and just rely on our settled intuitions about specific cases. But is that really possible? The analytical impulse seems hard to resist. Even if we haven't found the definitive answer, the process of evaluating different proposals, identifying their strengths and weaknesses, represents genuine progress. The enduring fascination with truth-likeness stems from its deep connection to the very practice of science, our understanding of knowledge, and our metaphysical assumptions about the nature of reality, particularly concerning realism, fallibilism, and what it means for a theory to be getting closer to the truth. If you'd like to delve deeper into the intricate debates surrounding truth-likeness, Popper's own works are essential starting points. Ninluto's comprehensive book provides a detailed survey of the early debates, while Kuiper's book offers a platform for different viewpoints. Both Ninluto and Zwart have more recent surveys that critically examine developments, including various hybrid approaches. These texts should provide a solid foundation for anyone wishing to engage with this challenging and important philosophical problem.